Hello grade 12s, welcome to my channel. Hopefully you are all good. So let's look at trigonometry, specifically trigonometric identities. Where do these come from? So obviously guys, we look at something like the Cartesian plane, right? Doesn't look exactly vertical. That's much better. So this is all built on a right-angled triangle, and we have the origin there. So if we have a terminal arm, at this point we're not interested in its size, so we can just drop a vertical line down. Okay, so obviously what was not drawn is a mere construction. So we've got this terminal arm, right? We can call it OP if we like, but let's not name anything. And let's call this angle theta. Okay? So on a Cartesian plane, when we have this, we know the adjacent is going to be x, essentially, and the vertical is going to be y, isn't it? Yes, because let's just say this is P with x and y coordinates. Now we know that the trig ratios are built from this right-angled triangle, such that, number one, cos of theta is defined as the adjacent over hypotenuse. And of course we call the hypotenuse r. I forgot to label it. And then this is going to be equal to, okay, let's not do it there, it's not quite nice. So this is equal to, adjacent is the x at P. So this is x over r, which is OP. That is essentially the cos of theta. So that's number one. Number two, we know that the sine of theta is defined as the opposite side over the hypotenuse side. Right. Therefore, our sine theta is equal to, the opposite side is now y. So we have y over the hypotenuse side, which is r. These are very important things to remember on a Cartesian plane. The third one is to notice that the tangent of theta is the opposite over adjacent. Okay, now this tells us that tan theta is actually y over x. So these are very important. You guys don't do the reciprocals, it seems, nowadays. We used to do the reciprocals, but I'm not going to go into them since you guys don't seem to go into that. So from that Cartesian plane, this is what we can gather, guys. Okay? This is what we can gather. So we need to remember this at all times. Here we have not put any lengths into this thing. And we know this is grade 11 work. And from here, we notice something. If we look at this right-angled triangle, Pythagoras tells us something, you know? Now, this is notes. Note number one, we know that essentially x squared plus y squared is equal to r squared, right? This is just knowledge of Pythagoras. This is from Pythagoras theorem. In a right angled triangle, this is it. This you proved in grade 9, I believe. But, okay, we did it in grade 9. But you guys may have done it elsewhere, so it's not a big deal. Now, what can we do? What happens when we divide by y throughout? Remember, in maths, we can divide by anything we want, as well as we can multiply by anything we want on equation. When we divide by y, let's just say y squared, sorry. So we get x squared over y squared plus y squared. What am I doing now? Goodness. I'm not doing anything right. I want to divide by r squared. Okay, we can divide by anything that we want. So this is going to be r squared y over r squared equals r squared over r squared. Of course, mathematically these ones will do us the honors. So this implies that we've got, here we can simplify using exponential rules. So all of this gets to go to the exponent of 2, which is y over r squared. This is equal to 1. Okay, I don't like when things don't align so well. So this is what we have. Okay, now what did we say? What is x over r? It's cos. So we've got cos theta all squared. What is y over r? It's sine theta all squared equals 1. And therefore we will see that cos squared theta plus sine squared theta is 1. And this is the identity that we need to know. We call it the square identity. Obviously, guys, you don't seem to do reciprocals. So in this identity, we could divide by cos squared theta to create another identity. We can do a whole lot of things. So these are some of the things, guys, that need to be cemented in your brains. Because for me, it always helps to know where things come from, rather than to just use carelessly. Because when the question is tricky, it demands this very basic knowledge. And sometimes you guys miss it because you never understood where these things came from. So this is our first note from grade 11. Now the second note is that we can do this and say, technically, let us do something like this. Now I want us to play a very smart game because we need to identify something, okay? We need to identify something great. Okay, maybe let's not identify, let's just do it. What happens when we take sine of theta and divide it by cos of theta? What do we get? Sine of theta is y over r. This is divided by x over r. Okay. Now, this is the same as y over r divided by x over r. ne? And then we come to it and say this is still y over r times r over x, because that's what we do. And guess what? Those ones will divide to 1 so that the remaining fraction is y over x. But now what is y over x here? It's tan theta. So we know that basically you can easily say this implies that sine theta over cos theta is what it is. Okay. Here we can say therefore sine of theta over cos of theta is actually tan theta. This is the tan identity that we need to know. We need to know. So this is one of the things that we have to understand, guys. So from here, instead of just doing this, essentially, instead of just doing this, one can easily just do that by perhaps dividing sine of theta by cos of theta. One can actually take this definition, because we can divide by anything. Whatever we divide by, we must divide by on the other hand as well. So there are many ways. I just didn't want to kind of startle you. But if you think about it, this is how this actually was noticed. Because in maths, we just play with the tricks. But since you guys no longer do what we call reciprocals, I don't know why they took them out. But I will just show you. Technically, we could have taken sine theta, giving us y over x. In maths, we can decide to multiply by 1 over cos theta, or we can just say, in maths, we can divide by anything. So if we divide by cos theta, and so we should be doing the same here, isn't it? So this would imply that sine theta over cos theta is going to be y over x divided by what is cos of theta is x over, why did I say sine? This is r, man, goodness. This guy is becoming sloppy. Okay, sorry guys for this, but I just want to take you guys through this nicely. And can you see it just sorts itself out? Sine theta over cos theta is equal to y over r times r over x. And these two do it. And then we will have sine theta over cos theta as y over r, not r but x, which is equal to tan theta. So so that's the conclusion. So technically, as I said, we can divide by anything in maths as long as we essentially want to do anything. If we have an equation, which we will see by an equal sign, if we do something to the left hand side, we also do it to the right hand side. Because sometimes you got to understand that it's not a matter of just forcing it here, because it looks as if we forced it here. Essentially, we just took an already existing definition and decided to say, what happens if we do this? What do we get? Even with reciprocals, you will see that we can do a whole lot of things that we want. It can lead us to more and more and more and more. So guys, I just wanted you guys to understand where the square identity comes from. So this is called the square identity. The square identity. And this is the tan identity. Maybe let's leave it as tan identity. Okay. So those are the two identities from grade 11. Please guys, know how this is done and play with it. Okay, play with it. Play with these things. Even play with the square identity and see how many other square identities you can create of the reciprocals. All right, because there's plenty of them. There's plenty of them. Okay. There's one for sec squared, there's one for cosec squared, there's one for cot squared. So there's a whole lot one can create up there. So play with those, as they may just be very useful later on. I don't know why these were taken off the syllabus. The syllabus has to be packed, guys, so that we have a lot of space to examine you, rather than to examine you on just simple things. You end up thinking you know the subject when you actually don't. Okay, so that's it, guys. So that's the tan identity and the square identity, and also the definitions of the trig ratios. So we call these ones the trig ratios, trigonometric ratios, and this would be the identities that we learned from grade 10. Now let's get to more grade 12 focused identities. We're talking about compound. Okay, let's write it better. Compound angle identities. I don't know why my hand is so impatient, guys. My hand lately, identities. My hand is so impatient. I end up pulling it. I don't know why. Always working under pressure is detrimental to the writing. So let's talk about these compound angle identities. Again, where do they come from? Well, we know that there's this one that we call the generic compound angle identity, which gives us everything we want. So we know that cos of angle A minus angle B is going to be equal to cos of the first angle times the cos of the second angle. The sign changes to plus. Sine of the first angle, sine of the second angle. Okay, so this is the generic identity that gives us everything. Okay, it gives us everything. In fact, we may even stretch this and say compound angle identities and double angle identities. Okay, because in grade 12 you get introduced into this. Again, I know most teachers just tell you this, go through it, and you just go through it, but it's nice to know where do they come from. Now, to get this done, how do we do it? Well, on a Cartesian plane, first of all, we can draw ourselves a nice Cartesian plane. Okay. So this is going to be x, this is going to be y, and that's the origin. Let's say we draw a unit circle. Now that's very important. We need to draw a unit circle. What is a unit circle? It's a circle with a radius of 1. Okay, we will assume this is a unit circle. So what I call this, we call this thing a unit circle. Why? Because it has a radius of 1 unit. Whatever it is, the units that we're using, so we call it a unit circle. Please guys, remember this, it's very important. Okay, now this unit circle of ours, we can just draw ourselves that radius right there. We can call this point of intersection with the circle as, say, let's say P. Okay, and then we can still draw the unit circle into a second quadrant just for the vibes. We could easily draw it in the first quadrant, but just to give it space, we can call this one point Q. Obviously, point P has x and y because it's on the Cartesian plane, same as point Q. It has x and y coordinates. Now, like we know how to do this, we just drop it down and say, cool. We drop those down to the Cartesian, to the x-axis, so that we've got a whatever. We've got these right-angled triangles. And of course, anything that we introduced, we break it up to show that it was not necessarily there. It wasn't given. And remember, this is a unit circle, so this is 1 unit. And so this is 1 unit. Nice and easy. So we can call this angle B. Let's call it angle B. And we call this obtuse angle here angle A. Alright, so we've got the obtuse angle A, the acute angle B. Now, we can also construct, we can join PQ. But since it was not there, we break it up to show that that is the construction. Now you'll notice 3 triangles here. So as you can see, we've got this cream white. If this is cream white, I don't know what color this is. And then the yellow one, some people will say gold. This is green. Okay. Now that's a proper green. It's not light blue. This is green. Now I've got these 3 triangles. So what we're interested in are the coordinates at P. What are those coordinates at P and Q? Well, if we look at, say for example, this side, we will appreciate that essentially sine of angle B is going to be opposite, that's the y there, over hypotenuse, which is 1. Okay, so if we cross multiply here, what do we get? We see that y is going to just be sine of angle B. So we know that our y here is sine of angle B. And if we look at cos of angle B, we'll see that it's going to be x over 1. If we cross multiply there, what do we get? We get that x is equal to just cos b. And so that's the x coordinate here. So those are the coordinates at P. Please know these things, guys. Very important stuff. It's not far-fetched. Let's look at Q. If we do the same for Q and say cos of this angle angle A is going to be the x over the hypotenuse, which is 1. Then we cross multiply there. We see that x is going to be essentially cos A. So this is just cos of angle A. And we can say sine of A is going to be equal to y over 1. We cross multiply. We'll see that y is essentially sine A. Maybe we can say y at Q, x at Q, y at B, at P, x at P, so that we are clear as to what we are using this for. So we know that here we've got sine of angle A. So those are the coordinates. Those are the coordinates of what we have over there. So I'm sure you can see that this is not so difficult. But now, guys, what are we interested in? We want to know A minus B, right? We want to create that situation, but how do we get around it? Now that we have worked with the green and the cream white, now we get into this triangle QOP or POQ. We will get there and say in triangle POQ. Now we can see that we know that this side is given, that side is given. We don't know that side. We can use the cosine rule from grade 11. So we know that essentially PQ squared is equal to OP squared plus OQ squared minus 2 times OQ times cos of the angle. See, this is A minus beta. Not beta, but A minus B. Because then it gives us this angle. Okay? So that angle is going to be the obtuse angle minus the acute angle. It leaves us that angle. So we can see something here. So this implies that PQ is, this is 1 squared plus 1 squared minus 2 into 1 times cos of angle A minus angle B. Now we continue. We know that PQ squared is equal to, this is just 2 minus 2 cos of angle A minus B. We cannot simplify further here. We stop here. Okay? So this is our first equation using the cosine rule. Okay? That's why we know this. In that particular triangle we specified. We know also that in the same triangle, PQ squared, using the distance formula, it's going to be the x at Q minus x at P all squared plus y at Q minus y at P all squared. Why do we know this? This is the distance formula. And by the way, it comes from Pythagoras. There's many ways of showing this, but let's not get to that now, just to avoid unnecessary problems. This is introduced as far back as grade 10, seemingly these days. It was introduced to us at grade 11, back in the days. Okay, we're gonna keep giving you the history. All right, so this implies that PQ squared, now x at Q, what is it? It's it's cos A, minus x at P, that was cos B, all squared, plus this is sine A minus sine B, all squared. We just plug those coordinates in there, no problem. So this implies that PQ squared is equal to, we expand this, it's going to be cos squared A minus 2 cos A cos B plus cos squared B, right? Right. Plus this is going to be sine squared A minus 2 sine A sine B plus sine squared B, all right, good. So now we know, guys, that essentially cos squared a particular angle plus sine squared of that same exact angle, from what? From our square identity. We know that when the angle is the same and we are taking sine and cos squared, adding them together, what do they give us? 1. So we know that these two, this is PQ squared, is equal to, now this and that gives us just 1, plus we also know that cos squared a particular angle plus sine squared a particular angle, as long as the angle is the same, we get 1. Now we have minus 2 cos A cos B minus 2 sine A sine B. So that's what we have left. Now we continue. PQ squared is 1 plus 1 is 2 minus 2 cos A cos B minus 2 sine A sine B. Now we cannot go further than this, so we will make this equation 2. But notice one thing, this is PQ squared, this is still PQ squared, so these are simultaneous equations. That's why we learn these in algebra, so we can equate the two. So we can say then, we know that 2 minus 2 cos A minus B is equal to 2 minus 2 cos A cos B minus 2 sine A sine B, because these two are essentially giving us the same story. We know that equation 1 is equal to equation 2. That's what it is. Now guys, we will see that when we transpose, if those two numbers are the same sign on either side of the equal sign, they will cancel, because as we transpose one to the other, it cancels out. So what do we have? This implies that we've got minus 2 cos angle A minus angle B equal to minus 2 cos A cos B minus 2 sine A sine B. All right. Now we can see minus 2 is a common factor. We divide by minus 2 throughout. So what do we get? Cos A minus cos B. This becomes positive cos A cos B. This becomes plus sine A sine B. And indeed, we've got our identity. Nice and easy. So this is essentially the basis to all of what we're doing. Can you see it's not such a bad thing? It's all that which we know, but sometimes we don't care to look at constructively. So the concept of simultaneous equations gave us these identities. That's why these identities are true, because they're describing the same distance on the Cartesian plane. One using the cosine rule, one using the distance formula. Of course, with trig ratios included thereabout. So this is our generic identity. So this is our first compound angle identity, which is the one for cos. Okay, it's much easier. Now here's the second one. How do we do cos of angle A plus angle B? What is it? This is going to be equal to, but remember now we want to use this generic one. I would call it generic, but yeah, whatever. We want to use that because we don't know this and we don't want to struggle. If we find something in life, we tend to want to just use it. So how do we create this? This is the same as cos of angle A. We pull out a negative and it looks something like this. It's a mathematical trick so that we have this negative that we have there. Once we have it, we can then do that expansion nice and easy. So this is going to be cos of the first angle times cos of the second angle, right? Now the sign changes to a plus, sine of the first angle, sine of the second angle. Alright, so this also implies that cos of A plus B is equal to, this is still cos A times cos of a negative angle is just positive there, plus sine A, but sine of a negative angle is minus sine A. Okay, so what do we do there? We can say therefore cos A plus B is going to be cos A cos B. Now positive times negative is a negative, sine A sine B. So that is the cos compound angle identity for that situation. Now you will notice something, that when we have a plus here, the sign is a negative, but everything is the same as above. It's just the sign has changed now. As here it was negative and then the sign became positive. So that's all that changes. So this is what we can see. Now what about the sine compound angle identity? When we have sine of angle A minus angle B, what do we get? Well, how do we use that same concept? We know that sine and cos are co-ratios. So this is the same as the cos of 90 degrees minus A minus B. Right, because when we reduce this, it gives us exactly what we have. But now what is nice is that we've got this negative here. But this is a bit problematic because we don't want those angles together, so we're not yet done. So we will take it a step further and say this implies that sine of A minus B is going to be equal to cos of 90 degrees. Now we FOIL this out, it becomes A plus B. Okay, so this is what we have. When we break that, this also implies sine A minus B is equal to, now we want to group things. This is cos 90 degrees minus A. But now we notice that this sign becomes positive and we don't want it to be positive. So what are we going to do about it? Well, we will do what we know best. Okay, so we will take out the negative and leave the B like that. Easy. So now we have our target, exactly the cos where there's a negative, because then the expansion becomes just as easy. So we continue. Sine of A minus B is going to be cos of the first angle 90 degrees minus A times cos of the second angle. Then the sign becomes a plus. Sine of the first angle times sine of the second angle. Great. We continue. Sine of A minus B is equal to, now we've got co-ratios here. This goes to sine A cos B, because cos of a negative angle is positive, plus this becomes cos A into minus sine B. Sine of a negative angle is like that. So from here we know that sine of A minus B gives us sine of the first angle, the cos of the second angle. Negative times positive is a negative, cos of the first angle, sine of the second angle. So now this is the compound angle identity for essentially sine. So as you can see, we had to play a lot of mathematical tricks to get ourselves into the position of expanding using what I would call the generic identity. As you can see, we can put it on a Cartesian plane and play around it until we get it. That's why we make everything look like it, so that we can use that expansion. Now these things are very important, guys. They may look a bit exhausting to look at them, but please practice them so that they become second nature. Because certain questions that are of a higher order nature, they will require this piece of knowledge, knowing how to play with the signs to create something that you can identify and then use it to solve further. And you'll be surprised how far it can take you. Now let's do the last one for these compound angle identities. So we've got our fourth note. So we know that what happens when it's sine of A plus B. What then? Of course, we know this is the same as the cosine of 90 degrees minus A plus B. Okay, nice. And then I will take you through it nicely as well, because get used to some long, lengthy videos. It builds your endurance. Otherwise, you become weak. You know, you become weak if you don't endure. Sine of A plus B is equal to cos. Now we can group 90 degrees minus A and then minus B. This one, already the sign is how we like it. Mind you, this is just theta. As big as it is, it's just theta. Think about it that way. You will never get lost. So we can expand it the same way as we have been expanding, using that generic cos of the first angle times cos of the second angle. This time it's just b, so we don't worry. And then we know that the sign will change to sine of the first angle times sine of the second angle. Again, the second angle is just b. There's no need to worry about the signs now. So what are we doing? We are doing good. In fact, we can just make a conclusion here. Sine of a plus b is going to be, what is this? This is sine a using corratios times cos b plus, corratios here is going to be cos a sine b. And that's the identity when the situation is like that. So it helps to know how to derive these identities, guys, because trust me, when you get to higher order maths, it's going to hurt when you cannot picture things, or you do not know how to derive things by using what is identifiable. So these are the compound angle identities for cos. That's the first one, which we proved, used it as a generic or a template for the rest. And using that template, we got when the two angles are added, we got to sine. When the angles are not added, can you see when it's negative? It's negative. But it's just sine cos. Sine of the first angle, cos of the second angle. Cos of the first angle, sine of the second angle. Same story here. You will see that the plus remains a plus with sine, but it's just that cos of the first angle, cos of the second angle are a product, and then cos of the first angle and sine of the second angle are also a product on the other side. Now I have shown you guys the 10 compound angle identity. I will not do the proof, but I will show you those identities. So we know that when we've got tan of a minus b, what do we have? We are going to have tan of the first angle minus tan of the second angle divided by 1 plus, this time, the product of tan of the first angle and tan of the second angle. I have shown you guys how this proof is done. See the video on this one. See a video in the channel. Hi guys, my writing, I don't know what am I gonna do because I'm so used to writing in a hurry. See a video in the channel. Doch, man. It's not right, man. It's not right. So for the 10, you guys don't seem to be required to do this. You are just told whenever you see 10, use sine and cos. And in fact, it comes exactly from those cosine and the sine compound angle identities. This is what we end up with. Figure it out. If you don't want to watch that video, it may come to haunt you, I tell you. So what happens when it's 10? Come on, man. Can you write well? 10 of a plus b. This one is going to be 10 a plus 10b. So this is easy to cram. If it's a plus on the numerator, we're adding the tens of the two angles. Here it's going to be 1 minus the product of the tans of those angles. Easy, guys. Easy, 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 easy. There is nothing that you must cram here. Okay, cram it if you want, but the proofs are interesting. Very nice. Very nice stuff. So with us, we were not given these ones in the information sheet. And actually, these were examinable. Those were the 2 compound angle identities that were examinable, because they were never provided in the information sheet, but they were required. As you will see on the videos that I did for the paper I wrote in 2005, you will see that the 10 compound angle identity or double angle identity came up. And essentially, it happened also for some paper I did later on. I'm not so sure, but I did a paper, whether 2006 or 7, but one of them. I did a paper too there. You will see that proof came up. If not necessarily the proof, but perhaps the application. So I just wanted you guys to know this, but please, these ones, there's a video for these 2 on the channel. So check it out. You will learn. In fact, I don't think I did both of them, but you can try yourself the second one. It will give you a perspective. Now let's talk about the double angle identities. Now these double angle identities, guys, are nothing but compound angle identities, where the 2 angles are actually equal. So this one is easy. The first one is going to be cos 2x, for example, or maybe let's say 2 theta. Theta is much more nicer. Cos 2 theta is going to be the same as cos of basically theta plus theta, right? But now we don't know this. Okay, we can say we do now, because we know when the angles are added together for cos, what is the story now, right? We can use this identity. It's up to us, honestly. Or we can use the generic, but I often like the generic, but it complicates things. So we will see that essentially this implies that cos 2 theta is equal to, now it's going to be cos of the first angle theta times cos of the second angle theta. Then the sign changes to minus, right? Right. The sine of the first angle times the sine of the second angle. And the good thing is that the angle is the same. So this implies that we've got cos 2 theta is equal to, this is cos squared theta minus sine squared theta, because that product is a square. And of course, this is the generic compound angle identity for cos. But using our square identities, we can change cos to sine, and we can change sine to cos, depending on what we are trying to achieve. All right? So at some point, when we change cos to sine, what do we get? We will get, this is 1 minus sine squared theta using our compound angle identities, which is going to be 1 minus 2 sine squared theta. If we decided to use we decided to change that, this is the same as cos squared theta minus 1 into 1 minus cos squared theta, right? So this is cos squared theta minus 1 plus cos squared theta. FOIL method, so like terms, we get 2 cos squared theta minus 1. Okay, so these are the derivatives of what we just did. So we can choose to expand cos 2 theta. Cos 2 theta is like that. Actually, let's not say it implies. This is a conclusion. And we can say cos 2 theta can be expanded this way or this other way. Okay? So please know these ones. They are commonly asked, and in fact, they are given on the information sheet. And as you can see, these double angle identities just came from the compound angle identities that we know. All right, so the second one for sine, so we will have sine of 2 theta. Now what do we know? Sine is going to be the same as sine of theta plus theta. So we can use the sine expansion. We don't need the generic cos expansion. So sine 2 theta, because now we have those identities. So this is going to be sine of the first angle, cos of the second angle, plus sine of the second angle, cos, sorry, there's a mistake here. There's always an alternation. It's cos of the second angle, of cos of the first angle, sine of the second angle, whatever. Now, we will see that these are actually like terms, but we need to arrange them so that it's easy. So this is sine theta cos theta, plus this product. We can just show that this is the same thing repeated twice. And so we can say sine 2 theta is going to be, these are like terms, right? Now, this gives us 2 sine theta cos theta. And that's the double angle identity for sine. And luckily, there is only one. There's not 3 like in the cosine situation. Now let's give you the extras. Again, these ones you can explore for yourself. What happens to tan of 2 theta? This is going to be basically 2 tan theta divided by 1 minus tan squared theta. Easy, ne? Yeah, that's very easy. And that's it. That's it. Again, explore this one for yourself. Derive it by using sine and cos, using the video that I showed you guys. So this is what I wanted to discuss with you guys. Please watch this video during the day or late afternoon, because at 7 we are going to have a lesson where we are going to apply all of this basic knowledge. I just wanted to do this video prior to the lesson because we were supposed to have this lesson on Saturday. You guys didn't attend, but I'm aware that there is load shedding in the country, so unfortunately it may have affected your attendance. But anyway, guys, please look at these things. They are there in your textbooks. What I'm showing you guys, it's not something new. It's something that you already know. But I just wanted to remind you so that as we go into this, because I know some teachers skip these earlier portions of these topics. They just rush into applications because they just want you guys to be ready for the exam, but they don't realize the mistake of assuming that you will grasp these. Some students fail to use these properly because they don't even know where they come from. Students like myself would always struggle when I don't know where things come from, because I'd be like, but how is it true? So if you're battling with this thing and I have my own ideas as to how it should be perhaps, then I fail to see how to use it comfortably. But when you know where it comes from, you actually become comfortable using it. So I hope you guys are good and you have learned something, and if not, well, it's not too bad, because we're going to get into a proper lesson where we are going to apply this knowledge. Otherwise, guys, leave a thumbs up and goodbye. I'll see you again next time.